122 acres of campus area, Manipal University, Jaipur aims to unleash the student's potential and transform him into a globally accepted personality. With its heritage excellence in higher education, and within a short span of time, it has ascended itself at a global scale. It is the only private campus in the Rajasthan district that owns a flag of its own. Besides offering a wide choice of multidisciplinary programs, Manipal University is a domain to more than 6,400 students from varied social backgrounds. Manipal University, Jaipur has something excellent to offer to every student. Engineering or basic sciences, journalism and mass communications, arts and law, architecture or design, management and commerce. It helps build a global leader out of every student. This university has been awarded with the Smart Digital Campus by Cisco for building the first digital campus of the country. The education here is not confined to books and classrooms. Rather, it personifies the personality and sharpens a student's skills. The university aims to fabricate the centers of brilliance for research and innovation, considering research and development as the integral part to prosper creations of the great innovations of the university and its students. A fully Wi-Fi enabled campus, state-of-the-art digital library, comfortable hostels, well equipped with the latest hardware and software laboratories, multi-cuisine cafeteria, club area, game zone. MUJ is another home for students. The Manipal University, Jaipur is designed by the prominent architect Hafiz Contractor, and it owns Yoho, the youth hostel. Students who go for hostel accommodation enjoy the Yoho living experience in addition to the convenience of being right next to the university. Yoho stands for much more than just hostels. It provides safe and comfortable environs both inside and outside the rooms. 850 kilowatt solar power machines are installed on the university terrace area for using sunlight for as many activities as it can. It has been awarded with the Lead Indian Platinum Award for Energy Conservation and Environment Design. The event calendar provides for plethora of music, dance art and festivities that there is an aura of celebrations around the campus. The university holds special annual fests, Annual Day celebration wherein students can enjoy the different cultural activities and showcase their talent. The farewell party for the students is also organized by the university to bid them warm goodbye and wishes. Manipal University, Jaipur is synonymous with excellence in higher education. It thrives to sum up the vast ocean of knowledge and provide an experience to the students where education is celebration.
Hello everyone, I'm Jaiti Agnihotri. I did my Bachelor in Science from Manipal University, Jaipur. In Manipal University, Jaipur, exposure is being provided to every single student, and faculty make sure that students work on their weaknesses. All the faculties, including HODs, Dean and Directors, are easily approachable, And this was the main reason that I had also done my masters in mathematics from Department of Mathematics and Statistics. I will also be pursuing my PhD from the same department. Every year, placement drive is being conducted by renowned companies for students of BSc and MSc, and they make sure that students get placed according to their caliber. At the end, I would like to thank all my faculties, including HOD, Dean, and Director, for bringing a positive change in my personality and being supportive throughout the journey of Manipal. Thank you.
Hello everybody, my name is Preeti and I am graduate in mathematics from Manipal University Jaipur, batch 2018. Well, I was hostler and I have spent 3 years full of learning and experiences, and it has been an amazing journey that I have always dreamed of. Department of Mathematics offers an opportunity to learn and grow with faculty members, supportive faculty members, and it also offers an amazing learning experience through its regular lectures, class activities, workshops, and guest lectures. Manipal University offers various platforms other than academic, such as Culture Fest, Sports Fest, and some other events that helps us to improve at personal and professional levels. The faculty member also helps us to acquire a conceptual understanding of nature and structure of mathematics and its applications. And the Department of Mathematics also offers various softwares to learn the application of mathematics and statistics in practical life. Well, in the end, I would like to express my gratitude towards head of department and faculty members for providing me this wonderful experience. Thank you.
Hi, I am Chaudhary, student of BSc Mathematics Honours of batch 2015 to 2018. I completed my graduation from Manipal University. I got good grades, and apart from that practical knowledge, that was because of the hardship of our teachers who always motivated me in becoming a good person. In our university, especially in mathematics and statistics department, they did not teach us only through books, but they always conducted lab practicals so that they can enhance our knowledge. And I spent the best 3 years of my life here.
122 acres of campus area, Manipal University, Jaipur aims to unleash the student's potential and transform him into a globally accepted personality. With its heritage excellence in higher education, and within a short span of time, it has ascended itself at a global scale. It is the only private campus in the Rajasthan district that owns a flag of its own. Besides offering a wide choice of multidisciplinary programs, Manipal University is a domain to more than 6,400 students from varied social backgrounds. Manipal University, Jaipur has something excellent to offer to every student. Engineering or basic sciences, journalism and mass communications, arts and law, architecture or design, management and commerce. It helps build a global leader out of every student. This university has been awarded with the Smart Digital Campus by Cisco for building the first digital campus of the country. The education here is not confined to books and classrooms. Rather, it personifies the personality and sharpens a student's skills. The university aims to fabricate the centers of brilliance for research and innovation. considering research and development as the integral part to prosper creations, the great innovations of the university and its students. A fully Wi-Fi enabled campus, state-of-the-art digital library, comfortable hostels, well equipped with the latest hardware and software laboratories, multi-cuisine cafeteria, club area, game zone. MUJ is another home for students.
Hello, sir. Hello, sir.
Good afternoon, sir.
The Manipal University Jaipur is designed by the prominent
afternoon.
architect Hafiz Contractor, and it owns Yoho, the youth hostel. Students who go for hostel accommodation enjoy the Yoho living experience in addition to the convenience of being right next to the university. Yoho stands for much more than just hostels. It provides safe and comfortable environs both inside and outside the rooms. 850 kilowatt solar power machines are installed on the university terrace area for using sunlight for as many activities as it can. It has been awarded with the Lead Indian Platinum Award for Energy Conservation and Environment Design. The event calendar provides for plethora of music, dance art and festivities that there is an aura of celebrations around the campus. The university holds special annual fests, annual day celebration wherein students can enjoy the different cultural activities and showcase their talent. The farewell party for the students is also organized by the university to bid them warm goodbye and wishes. Manipal University Jaipur is synonymous with excellence in higher education. It thrives to sum up the vast ocean of knowledge and provide an experience to the students where education is celebration.
Hello everyone, I'm Jaipur Agnihotri. I did my Bachelor in Science from Manipal University, Jaipur. In Manipal University, Jaipur, exposure is being provided to every single student, and faculty make sure that students work on their weaknesses. All the faculties, including HODs, Dean and Directors, are easily approachable. And this was the main reason that I had also done my Masters in Mathematics from Department of Mathematics and Statistics. I will also be pursuing my PhD from the same department. Every year, placement drive is being conducted by renowned companies for students of BSc and MSc, and they make sure that students get placed according to their caliber. At the end, I would like to thank all my faculties, including HOD, Dean and Director, for bringing a positive change in my personality and being supportive throughout the journey of Manipal. Thank you.
Hi, I'm Chaudhary, student of BSc Mathematics Honours of Batch 2015 to 2018. I completed my graduation from Manipal University. I got good grades, and apart from that practical knowledge, that was because of the hardship of our teachers who always motivated me in becoming a good person. In our university, especially in mathematics and statistics department, they did not teach us only through books, but they always conducted lab practicals so that they can enhance our knowledge. And I spent the best 3 years of my life here.
हम ऐसे ही करना स्टार्ट करो Okay, Namaskar. Good afternoon to all of you. I, Giriraj Methi, on behalf of Department of Mathematics and Statistics, Manipal University, Jaipur, hearty welcome all of you for the webinar on the theme Numerical and Scientific Computing, which involves development, analysis, and execution of computational algorithms to solve mathematical problems from science and engineering. The one of the ingredient to construct physical problems are knowledge of multi-scale analysis of ordinary differential equations, partial differential equations, functional differential equations, fuzzy and fractional differential equations. Participants in our earlier webinar, Professor Harish Kumar from IIT Delhi delivered a talk on shallow water equations, applications to dam break and tsunami predictions. In continuation to that series, in today's webinar, renowned mathematician Professor A.K. Nanda Kumaran from Indian Institute of Science, Bangalore, will deliver a talk on an introduction to multi-scale analysis and theory of homogenization. And Dr. Joseph Rebenda from Brno University of Technology, Czech Republic, will deliver a talk on ordinary, partial, functional, fractional, fuzzy, a survey on applications of differential transformation. I am personally very thankful to Professor A.K. Nanda Kumaran sir and Dr. Joseph Rebenda sir for sparing their valuable time for our webinar. Now I invite Dean Faculty of Science, Professor Anup Kumar Mukhopadhyay sir. Over to you, sir.
Thank you. I hope I am audible.
Yes, sir.
Okay. Good afternoon, one and all. Our Chancellor, Professor K. Ramnaran, our President, Professor G.K. Prabhu, our Pro-President, Professor N.N. Sharma, our Registrar, Professor H. Ravishankar Kamath, Director, School of Basic Science, Professor Larita Ridwani, Head of Department of Mathematics and Statistics, Professor Kalpana Sharma, and on my personal behalf, I extend the hearty welcome to our speakers today, Professor Nanda Kumaran and Professor Joseph. We are very grateful and truly grateful to you, sir, because in spite of your busy schedule, you could spare few moments this afternoon with us. The subject of this webinar is very interesting. Physics and mathematics, I'm basically from physics background. Physics and mathematics kind of go hand in hand. And numerical computation as well as soft computing techniques are very close to my heart personally as a researcher. And also, I believe that they can do almost anything given the scope and chances, and once the algorithms are properly developed. And there are many complex problems, including the prediction of this pandemic. In many cases, they're being applied, and in fact, our space exploration, our Earth exploration by ONGC, and in geospatial exploration, in all such cases, the application of such numerical and computational techniques to derive data from images also is very important. Also, in the case of uh, deep level physics, where multi-scale modeling is very much necessary, particularly for large hadron colliders where numerous fundamental particles are produced. So therefore, this is an area which has many fallout, and I'm sure that all the participants who are attending this will be definitely benefited by the deliberations that be given by the experts. I'm also very grateful to Professor Sharma for infusing our faculty here, particularly Professor Giriraj Methi, Professor Vivek, and our all colleagues here from the mathematics. They are continuously doing very good quality webinars and sensitizing people about all the possibilities that we can offer at Manipal University, Jaipur. I believe that this webinar will be very fruitful and very useful to all. Before I finish, I once again put on record our sincere thanks to APG Authority for giving us this platform. Also, my sincere thanks to the speakers for accepting our invitation, and my sincere thanks to the organizers for giving this opportunity to interact with all of you. Thank you once again. Goodbye.
Thank you, sir. Now I invite Director, School of Basic Sciences, Professor Lalita Ledwani. Over to you, ma'am.
Thank you, Dr. Giriraj. Namaskar and best greetings to each one of you. At the outset, I would wish to thank speakers of today's event, Professor A.K. Nanda Kumaran from Indian Institute of Science, Bangalore, and Professor Joseph Rabinda from Brno University of Technology, Czech Republic, for giving their consent to share their thoughts, experiences, and findings of their research work with the participants. I am sure that this webinar and proceedings of this webinar will be extremely beneficial to each one of us. And in this current pandemic situation, we all are facing unprecedented challenge, and it is very important to deliberate upon scientific and technological solutions that can help us to overcome this problem. And I'm sure that the conduction of such webinars and events using virtual modes will certainly help us to think and to learn what are the new ways by which we can overcome this crisis. And I'm sure with the experience and thoughts which will be shared by esteemed speakers in today's event will certainly help us not only in gaining new knowledge, but also it can help all the faculty members and participants attending this webinar to think about the solutions which is based on theme of this webinar, and they can certainly come up with their out-of-the-box ideas that can not only help us at professional front, but subsequently it can help us to uplift people all over society. And I also take this opportunity to thank Professor Anup Kumar Mukhopadhyay, Dean Faculty of Science, Manipal University, Jaipur, for his constant support, encouragement, and because of his guidance and encouragement, we are able to conduct a number of events since March 2020. On different themes, not only based on COVID-19, but other themes which are directly or indirectly linked with facing this pandemic situation. Thank you so much, sir, for all your support and guidance. I also wish to thank Mathematics and Stats Department, Manipal University, Jaipur, with a special note to HOD Dr. Kalpana Sharma and conveners Dr. Giriraj Methi, Dr. Vivek Singh and Dr. Rishikesh Dutt Tiwari for taking this initiative to conduct webinar on very important theme, that is on numerical and scientific computing. I think it is the need of the hour to talk about and to deliberate about this topic. I would take this opportunity to share some of the facts and findings of our school. The organizing department is the part of the School of Basic Sciences. So the School of Basic Sciences has started its functioning since the inception of the Manipal University, Jaipur, that is in year 2011. The school operates through 5 departments, that are Department of Biosciences, Department of Chemistry, Department of Computer Applications, and the organizing department itself, and the Department of Physics. A number of academic programs are being offered by the school. Good videos were playing before the conduction of this event. So BSc Honours program, MSc programs in various disciplines are being offered by the school apart from PhD program. And if you talk about activities which are being conducted on research front, we understand that teaching and learning process cannot be completed if we are not including what are the learning and findings which we are having at by doing different research activities. And in today's world, we can quantify our research work by number of publications in peer-reviewed quality journals and whatever funding we are having from different external agencies and patents. Keeping that aspect in mind, I would wish to share that what are the publications in short span of 4-5 years. I'm very pleased to mention that in last 5 years, we have published more than 350 publications in high quality journals. And if you talk about external grant which we have received from various national and international government and private funding agencies, then I am very pleased to mention that more than 4 crore rupees funding we have fetched from School of Basic Sciences from different funding agencies to work on different areas which is directly or indirectly linked with the societal activities, because we believe if we keep on working on basic research, that will not solve a purpose. So we are inclined towards working on applied areas also, and in current situation how this basic and applied things are correlated with the product development and computing. That is also very important, and I'm very happy that department has taken this initiative to conduct this webinar on this theme, which is the need of the hour. And the third point, apart from publications and funding, the third point, how actively we are conducting different academic events, that is also very important thing. So before this pandemic has started since March 2020, of course the platform was virtual since then. We used to conduct these activities using our campus facilities. So we used to conduct on a physical mode, but we are very happy to experience this, that the learning and findings which we have had using this virtual modes by the conduction of these webinars or conferences, it is at par with what we used to conduct in a physical mode. So, and every academician and researcher and everyone which is inclined towards conduction of these events, every person is realizing that this will not be stopped. The pace by which we are conducting events using virtual mode, that will be continued whether we overcome this problem. And I think this is the new learning which we all have experienced. So I'm very glad, and once again wish to thank department for taking this initiative, and again esteemed speakers who have given their consent. We are very happy and we are very enthusiastic to learn new findings which would be shared in today's event. Thank you so much. Hope proceedings of this event would be extremely beneficial to all participants. Stay safe. Thank you so much.
Thank you, madam. Now I invite Dr. Kalpana Sharma, Head Department of Mathematics and Statistics. Over to you, madam.
Thank you, Dr. Giriraj. Namaskar. Professor A.K. Nanda Kumaran, Department of Mathematics, Indian Institute of Science, Bangalore. Dr. Joseph Rebenda, Department of Mathematics, Brno University of Technology, Czech Republic. Chairman Professor Ram Narayan, President Professor G.K. Prabhu, Pro-President Professor N.N. Sharma, Registrar Professor H.S. Kamath, Dean Faculty of Science Professor Anup Mukhopadhyay, Director Professor Lalita Ledwani, Dean and Directors of different faculties, HODs, faculty members from different departments, and most importantly, dear participants. A very good afternoon to all of you. It's a great pleasure indeed for me to welcome all of you in this webinar on numerical and scientific computing. Main objective of this workshop is to make aware about different methodologies which is used for numerical and scientific computing. Simultaneously, I want to take this opportunity to brief you about the Department of Mathematics and Statistics. Department of Mathematics and Statistics was established in 2011 with an objective of offering world-class education and good research environment. At present, department is offering 3 programs, as Director Ma'am has said, BSc Honours in Mathematics, MSc in Mathematics, and along with this, PhD. The department strives for balance between teaching, research, and student development. Department is having qualified and committed faculty members. We are 23 in number, which provides quality education to promote research activity in core and allied areas of mathematics and statistics. The department enables students to excel in the area of pure as well as in applied mathematics and statistics. And I hope that this webinar will be a great help for all the participants. So I don't want to come in between the speaker and the participants. So once again, I extend a warm welcome to all of you in this webinar. Thank you very much. Over to Dr. Giriraj.
Okay, thank you. Let me share with you a brief introduction of today's first speaker, Professor A.K. Nanda Kumaran. Professor A.K. Nanda Kumaran received gold medal in MSc Mathematics from Calicut University. He did PhD from Tata Institute of Fundamental Research, Bangalore, and Indian Institute of Science, Bangalore. He is currently working as professor at Department of Mathematics, Indian Institute of Science, Bangalore. His research interest is partial differential equations, homogenization, analysis, controllability, and optimal control, tomographic reconstruction. Professor Nanda Kumaran received Sir C.V. Raman Young Scientist Karnataka State Award for Mathematics in 2003. Professor Nanda Kumaran is a fellow of National Academy of Sciences, India. He has supervised 11 PhD students and 2 are currently pursuing, and 10 postdoc students. He has published more than 100 research papers in international journal of repute and written many books on ordinary and partial differential equation with well-known publishers including Cambridge. Professor Nanda Kumaran prepared question papers for national level examination and visited many countries. Professor Nanda Kumaran is a member of American Mathematical Society, Ramanujan Mathematical Society, and many others. Professor Nanda Kumaran is on the editorial board of many reputed international journals. Professor Nanda Kumaran is a chairman of Board of Governors, TEQIP Phase 2, Government Engineering College, Palaghat, member KVPY Core Committee, convener Kishore Vigyanik Protsahan Yojana, regional coordinator, Karnataka Regional Mathematical Olympiad. Professor Nanda Kumaran is thesis examiner for various institutes and universities. Professor Nanda Kumaran served and presently serving Board of Studies of Department of Mathematics of many universities, including Gulbarga University, Bharatiya University, Coimbatore, Amrita Institute, Coimbatore, National College, Bangalore, Christ College, Bangalore, MS University, Baroda, Mount Carmel College, Bangalore, Central University, Kerala. We welcome you, sir. Today he will deliver a talk on an introduction to multi-scale analysis and theory of homogenization. Participants, if you have questions, kindly write to them in the chat box only. We will pick them at the end of the talk. Further, we will share feedback link at the end of the program. Over to you, Professor Nanda Kumaran, sir.
Okay, thank you. Can you hear me, all of you?
Yes, sir. Yes.
Okay, thank you, Dr. Giriraj, I'm honored to be invited for this seminar. And I appreciate during this lockdown you are organizing such a program and with the support of the department as well as the authorities of Manipal University. Quite often greater things are achieved during adverse situations. So you are presently having an adverse situation of COVID. Take this as an opportunity instead of thinking that we are facing bad thing. If you look at any great people, greater things are achieved during pandemic. If you ever recall Newton, he has done some of his work during the plague. So I hope some good results will come. Our things will get improved. Anyway, let me go to the lecture. So I will try to share it. Please let me know you are getting my. Can you see my?
Yes, sir. I see, sir.
Okay, fine. Is it in full screen mode?
Yes, sir. Still full screen mode, sir.
All right. So, as I already talked to Giriraj, the title doesn't exactly match the theme of your thing, because that is about numerics and computation. So I don't do any numerics and computation. It's a general theoretical talk. So my purpose is to introduce a very new research area which are not familiar to a majority of people in India. So I will be giving a very basic introduction. I will not be going to the advanced research in this area. By the end of it, some of the research papers from my area is enclosed with it. So to explain the research, you need to have little more maturity, and since this is a webinar and it's a kind of heterogeneous media, I have no idea exactly about the audience. So I thought it's better to give a very basic talk on this so that a majority of people can at least understand something. Anything more requires some specialization, so I should need a more knowledge about the audience to get into that. So the advanced things won't go into that. I'll present it in such a way even a master's student should understand most of my talk. So I will start with some physical models and examples, and then I will explain what is homogenization, both in a physical way. Physically, what does it mean? What in the application means? Why do you want to do homogenization? And then I will try to explain one or two mathematical difficulties. It's not that. Okay. So let's look at these pictures. It's basically a composite. So you have two colors you are seeing. If you see it in the second figure, first one is a one periodic cell. There are two materials. One is an yellow material, the other one is a red material. You can think it as gold and copper if you want it. So you are given fixed amount of two materials distributed in some periodic way. The distribution need not be periodic, it can be anything. But for the comfort and understanding it in a better way, I distribute the amount of material given here. But then you get something. I take the same amount of material, I distribute it in a smaller scale. So you see here may be distributed in the second figure, is distributed in an order 1 scale. The same amount, the total amount of yellow material or the total amount of red material is not changing. It's a two materials. So that is called the volume ratio of one material. So yellow divided by the total material is the volume ratio of the yellow material. The volume of the red material divided by the total volume with that. You get it. So I put it in a small scale. This is what multi-scale is coming into picture. Now I make the scaling much smaller. If it's a one scale it is distributed. Here it is the 1/4 scale it is distributed. Same amount. So if I go to the next scale, I will increase the scaling. If I become smaller and smaller scaling, that is that epsilon coming into picture, I get some changes happening. You see it's becoming distributed in a more fine scale. If I keep on doing this, the scaling becomes smaller and smaller. At the limit, I get a new material, what you call it a composite. You see, so you started with basically an yellow and red material. The end of it, the effective material, that means that if this is what we call it a mixing these two material at the microscopic scale. So you are becoming epsilon becomes smaller and smaller. So it's a kind of limiting process, and this is how you prepare composites. So you can ask, why do you want to make composites? That's important. Why do you want to do such a mixing? Why not work with the original material yellow and red? The reason is that the original materials will not have the desired property we would like to have. For example, you take the pure gold. When you take a pure gold of 24 karat, it's not possible to make any material. The property of the pure gold is so brittle that you cannot make any ornament using that. All of you know probably that. At least many of you are aware that with a pure 24 karat gold, you cannot make it because it will break it. You may not think it. But on the other hand, if you add some 10% or 20%, that's what we call it 22 karat, 23 karat, 20 karat material. If you add some 10% of copper or silver or aluminum, whatever it is, and you mix it, the moment you start mixing it and make it, for a layman, it still look like a gold material, but it is not gold, and you get entirely a new material. And that new material, you can make it a very thin wire if you want to do it, extremely thin wire. You see, suddenly, when you make a composite, mixing 2 or 3 material, end of it, you get a material which may have a property which we would like to have it. It's a one is it can the property which you may like to have may be vary. It may be some elastic property you want to understand. You want to understand the conductivity property. You may have a bad material in abundance, a good conducting material in small quantity, but then you want to have a large amount of reasonably conducting material. What do you do is that you take a not very good conducting material, mix with the conducting material, you get an effective material. It may have a better conductivity properties, a composite. There are many other applications. For example, you'll come to that. You may have a material. Normally, the heavy you want to have a very strong material, but the strong material are generally heavy. But then if you want to make a body of an aeroplane or something, you want to have a material which is very strong, but then you don't want to have a heavy weight. So you want some contrasting properties. One, you want a strong material, but not heavy. So this is how the composites are born. So this is not surprising. This is material scientists and engineers are creating such things for last several decades. You are all familiar with the plywood. The plywood is one of the material. There is not many pure strong material. You may not be able to. Sometimes it's expensive. Some material may not be available. Some material, even though heavy, you may not be able to make the things which you require. So if you look at the plywood, you see it's a kind of layers of material, which is what I'm saying, mixing it. You see the concrete. If you know that component material, it is never. There are other composites. I will show you some of the interesting property. So the composite structures are part and parcel of our daily life. Okay. Here is a very interesting material which I am showing only a microscopic view. This the picture which I am showing is not the layman view. It is a view of through a microscope, very, very powerful microscope. What I want to do is that normally if you have a material and if you try to pull that material in the lengthy direction, the width direction gets reduced. That's a natural thing. When you pull something, when you take an iron wire or something, if you pull it, you can see that the diameter is getting reduced. But I want to create a composite. When I pull it and increase the length, I want to also increase the width. Here is a microscopic structure. The structure is very interesting. The black part is the material part. Inside part is a vacuum. So these are only material in a different structure. You see, now you can view this. This is at the microscopic level. For a layman, you don't get to see this picture. Layman will get a material looks like a material. It doesn't look like it. He will not be able to see. We will not see the microstructure. What is at the atomic level? You have to go through a microscope. You see this. Suppose I pull this material at this point. If I pull this material at this point, it pulls this direction. If you pull this direction, this point and this point, the distance between this point and this point increases. So if I pull this whole material in this direction and in this direction, that is east and west direction, you see that the distance between these 2 points increases. When this distance increases, because it's a structure, the total width also will get increased. You would have seen this kind of structure in markets, etc. You take some iron wire, iron material, you just take some wire, make such a structure, pull it, you can see that it also increases. So if something happens at the microscope level, you will get a different material. So another thing, normally when the material, say iron, when it heats, it expands. But using the appropriate microstructure, when it heats, you can make that it decreases in volume. That's a very nice thing. Okay, this is a very interesting structure. When this is again at the microscopic level. All the structures which I am showing are at the microscopic level. You look at here, when you have a plain road, flat road, if you have a flat road, when you expand it, you will see. This you would have observed in the railway lines, etc. But if the material is little bent, something like that, in a low temperature, but you heat it, the bending increases. Now look at this picture on the right hand side. So if you heat it, the structure is created in such a way that it is bending to, it bends more. So if such a microscopic structure heats, the distance, this bends more, the bend more means this point and this point, the distance between this point and this point decrease. Similarly, the distance between this decreases because it will bend in this direction. Similarly, this. So all the distances between these 4 points decreases, effectively decreasing the volume. So you can create new materials by a microscope by doing a microstructure. So changing the scale. I'm not doing anything. You have to understand, it's only a physical rearrangement. There are no chemical reactions taking place to change the property of material. Even when gold and copper are mixed, it's only a physical mixing. There is no chemical interaction between the material. Still the property changes. That's what I want to convey to you. So these are the various microstructures available. Microstructure is available in nature also, like honeycomb structures, etc. Okay, you will see various structures and you can create newer and newer material to create different types of material. These are all engineers studied over last 50 to 70 years, various structures which they do it. So you can see these are all some structure. Explanation requires more and more time, which I will not do it right now. So this is only the picture of various composite structure, how to create new material. It's all the rearrangement where you put high conducting material. If you put high conducting material inside the core, and that effective conductivity will be different if you put the high conductivity in the outside the core inside that one. So the properties can be changed. This is very natural. As I said, this is the honeycomb structure. You know that about the honeycombs. So now this is one type of homogenization. So what effectively, in summary, I will come to that again. In summary, you will have a macroscopic structure, mixing structure. From the component material, you want to understand the effective property. As you said that you know gold and copper, you mix it. When you mix it, what is the effective property? You get it. So that's what homogenization will do that one. Let me describe you another important homogenization problem, physical part of it. Here is called a perforated domain. Before coming, this is a typical mathematical picture I am created. But then, if you look at the fluid flow underground, the fluid is not flowing through a pipe. The fluid is mixed with the solid particle. So there are a lot of solid particle. In between, there are perforations. So a lot of solid particle, and the fluid is flowing through that. So it is obstructed by the solid particle. So the equations which satisfies the normal fluid flow may not be satisfied by the fluid flow underground. So you want to know, so for example, outside, many of you probably are familiar with the Navier-Stokes equations and Stokes equations, the well-known equations. These equations may not be valid when the microstructure, so you have to see the microstructure accordingly. So it's a kind of homogeneous, these are called domains with the perforation. So you are studying problems in omega, not in a fixed domain, where in a domain there will be large number of holes. You remove that holes. So naturally, such problems cannot be handled numerically. That's what I want to say eventually. This is another third example, domains with oscillating boundary. So what I want to hear, these are the kind of work we are doing for the last 10 years. There are publications related to, you would have seen, many of you would have seen this. I don't know how many of you, that's why the direct class will, I can find out from the expression of the students, which I can't do it now. Okay, these figures you would have seen, these are heat radiators. When these systems are working, you would have seen in earlier computers, maybe now also you will see inside it generates heat, right? When it generates heat, it has to go out, it has to radiate. So these are all radiators. So the domains are not very natural domain. So you see, you will see a typical mathematical modeling. I will show you. So you may be studying your problems if you want to various equations or partial differential equation, ordinary or integral, all differential equations may not be in a very structured good domain, a domain with the complications, domains with the complexities of that domain. That gives you a different scale. So these are all jet engines, right? When you have a jet engine, it will have blades, and then the jet engine rotates, the blades are rotating. You know, when you put more and more blades, how it will rotate, and it can lead to complications. So these are all some. So mathematically, how do you model it? Mathematically, you have a domain here. You see, you have a domain that has no problem. On that, you can see this kind of large type of, this is exactly this picture. This is a section of that picture. You see, you have a domain here, a large number of pillars, that pillars whose width is very small. You see, the number of pillars increases in the same way. So naturally, there will be a small scale. So when you have a PDE to be studied in such a varying domain, you have to take care of a large number of boundary conditions. You see, all these are all boundaries, and definitely if this scale is going to be smaller than your parameter appear in numerics, you cannot take care of that one. So the smallness appearing in the problem is smaller than this scale which you can use it in numerics. Such problems cannot be directly attacked by the numerical thing. So that's why, so this is a three-dimensional version of that. You have a domain with a large number of pillars whose size of the pillar, not in height, the cross section of the pillar is very small. So you have another scale appearing there. I can show you that one. The same problem, same thing. Instead of rectangles, I have used it. So you see, you will have a domain with this one, and the width of the domain decreases. So it will become like that. It's exactly what I have. It's a goal there. So you have the number of boundaries increasing. You see. And if I take a much smaller scale, it will become like that. See, if the scale decreases, it looks like the region is filling up. So if I study a partial differential equation in this type of domain, and we are doing that such kind of partial differential equations in such domains, and this scale decreases, then what would be its limiting problem? So that's what homogenization. So you have a class of PDEs defined on a class of domains, and it goes there. But if you see, but there are gaps in between. Will it converge to a problem here? So you see, this is also another that is a very straightforward. In a circular domain, circular wheels, you will have a domain like that. This is typically that jet engine formulation done in the here. Okay, so there can have multi scales. That's a simpler geometry. So you have a more complicated geometry. These are all useful in many applications, okay? Nanoscales and other things, there are applications of this kind of domains which come into picture. So you have that. So these are all studied in the small oscillations. Okay, so that's my physical motivation about it. So that's a kind of basic introduction to homogenization in terms of the domain. So what will happen? So what are we study? What kind of problems we handle for mathematically? What kind of research? Research will not come into this talk because that needs much more. So the basically it is a study of macroscopic or bulk behavior. That means effective behavior. From the problem you have at the micro scale, you want to study a macroscopic, from the microscopic discussion, you want to get a macroscopic discussion. In other words, you have a family of PDEs eventually, and you will have a family of solutions, and then of the heterogeneous media, because heterogeneous media means there are more than one property. And then if you mix it, you get an effective material, it will have a property of a single material, whether heterogeneity is present only at the micro scale. The heterogeneities can be in the form of fine mixing of two or materials with different physical properties in the domain, or due to the singularities in the domain in the form of pores and granules. These are the examples which I have told you just now. You can study the properties, you can study structural, electromagnetic, thermal property. Accordingly, you will have different differential equation. Study of flow in a porous media like flow of oil, water through subsurface, pollution of groundwater, flow of resins and polymers and molds. So these are all will lead to this type of domains and the problems there. Analysis of vibrations of thin structure. Suppose you are creating very thin structure like a huge building, and that's a homogenization problem. If you look at it, forget about you create a structure with the pillars and what the other thing, right? With the pillar, whether that pillar is a small structure compared to the whole big structure. Okay, so that's a thin structure, the Eiffel Tower, many things. How will it vibrate? Will it reduce? And what kind of composites you use it? So it appears this homogenization has applications in several areas. Homogenization with oscillating boundary. As I said, these are all problems with oscillating boundary because these oscillations are happening in the boundary. Okay. The problem posed on the heterogeneous domain has a unique solution. All that is what is the nature of a typical problem. So you will have each epsilon small parameter, you will have a problem and you will have the study of that problem that may have a solution. The problem is that heterogeneities can cause the solution to develop high frequency oscillation. I will show you just one example where your trouble will come. I will show this. What is this second sentence? The issue is about the second. Because of this fine mixing, the solution will have trouble. The solution will develop high frequency oscillation. And it's difficult to handle high frequency oscillation. So a direct numerical study will not be able to capture either the bulk behavior or oscillations present as solution, which are at a microscopy. So the problem is that one. If you pose such a problem, if you are trying to take a limiting behavior, the parameter which you are going to zero can be much smaller than the discretization parameter. Naturally, you will not be able to capture using any numerical scheme. I will show you now. You look at your sin x. This is a typical sin x function. But what is this one? If I take sin x and then sin 2x, sin 3x, sin 4x, for example, this is sin 5x. So within the same distance, you have 5 periods. You see, sin 5 periods. Then this is sin 10x. This is sin 20x. So if I try to take, this is what I call a high frequency oscillation. So if I take that sin nx, with the sin x, sin 2x, sin 3x, sin 4x, like sin 100x. You can never capture sin 100 or 200x via any numerical scheme. So if you have a PDE problem, and if you pose a problem in such a high oscillating complex domain, your oscillation will have an inherent behavior like this. You may not know sin x, you know exactly, so you know that how is that behavior. But then you are getting a solution as part of a PDE. And that PDE, due to the complexities of the domain or complexities of the problem, the unknown solution will develop this type of high frequency oscillations. So how do you deal with that? You know that if you take sin nx does not even converge. So how do you study the limiting case? But it has a limit, you have seen it. When you mix gold and copper, end of it you are getting a material. But then when you are studying the problem and your solution, the solutions have a very high oscillating behavior. So how do you deal with it? On a physical ground, you have a limit. But on a mathematical ground, our usual mathematics, what you study at your MSc level, is not enough to handle this. You have to develop some new mathematics, which is available. That's what you have to study, advanced functional analysis. Okay. So do an asymptotic analysis, that we try to approximate the solution U epsilon corresponding to the heterogeneous domain for small epsilon by a solution of the homogeneous problem in which small parameter do not appear. So our wish, our aim is something important. You have an epsilon problem with epsilon very small. That's our physical problem. But then that physical problem cannot be solved even numerically. So what you do is that you are trying to approximate that physical problem at epsilon small by a problem for which this small parameter is not there, and solve numerically if you want that problem, or theoretically, and then approximate that. That's the aim. But then the difficulty, what I am trying to say is that this U epsilon, so solutions U epsilon will have this type of bad behavior. I can't call it a bad behavior. It is the behavior of your composite. And composites are important. So it's not a bad behavior as such, but for the present mathematics available to you may not be able to handle such behavior. But these are the physical behavior. Such kind of oscillatory behavior can be developed in the solution. So how do you handle? And you need the modern functional analysis. So the mathematical problem, what are the mathematical problem from this? To identify the limit equation. As I said, you have an issue. Identify the limit equation means you have a limit material, you got it. You have to understand. To prove the convergence of U epsilon corresponding to the heterogeneous equation to that of the homogeneous equation. And this is our one of the major issue. So you have to identify the limit equation. You have to identify the convergence. As I already told you, convergence has a problem. I will show you little more concrete soon in another level. To capture the oscillations of U epsilon known as characters. What is this high frequency oscillation? You want to understand the high frequency oscillation inherently present in U epsilon. How do you understand that? The solutions together with these oscillations characters can be used and computed numerically to get good approximation to the original solution. If you are not familiar with the PDE, don't worry. So this is a typical problem. You handle it. So you see, you have an oscillation. This is something like sin x over epsilon. When epsilon becomes smaller and smaller, this will behave like sin nx. You see, so you keep here sin x over epsilon. Sin index, when I say n becomes larger and larger, when it is a smaller, I take it below. Both effect is the same. When x over epsilon becomes smaller, 1 over epsilon becomes larger and larger. So if I, instead of sin aij of x over epsilon, if I put sine x over epsilon, when epsilon becomes smaller and smaller, this sine x over epsilon oscillates in a high frequency way. And that due to the oscillations in the coefficient, this u epsilons will also develop oscillation, which we do not know. That's the trouble. You are inputting some trouble into the problem, but then that trouble will give a trouble to the output. But then if you want to understand anything, you want to understand how exactly the troubles of your coefficients have transformed into the oscillation or high frequencies in u epsilon. This is what we call it a high frequency oscillation inherently present in u epsilon. So yeah, so this is we are considering a periodic structure at the microscopic level like composite material. Then epsilon will be very small, causing rapid oscillations in the coefficient and hence in the solution. This is what I am trying to explain to you. So question is, what's the homogeneous integral? So I'm not getting into the deeper difficulty. I want to tell you one general difficulty the mathematicians face in their analysis. Okay, in this context, if you do not know what is H1 now, don't worry about it. This you may have a problem. As I said, sin nx do not converge in your sense which you understand point wise. So what do I do with sin nx? This you can think it as sin nx. That's what I'm telling. But then the functional analysis is advanced so much, there is a concept of different type, rather there are different concepts of convergence in different spaces. One of the type of convergence is in a weak sense, what we call it a weak convergence. So the sin nx do not converge point wise, but sin nx will converge to something in a different setup. That is called, that's why you study normed linear spaces and various things in functional analysis. These are all developments. So what you see in functional analysis, the abstract notions are not really abstract. These abstract notions are introduced in functional analysis to carry out the practical problems. Okay, so there is a notion of whatever it is. If those who are familiar, there is a convergence. So whenever you have an oscillatory function, these oscillatory functions always will converge to its average. एक minute. अच्छा क्लासिला मते अच्छा क्लासिला. Okay, അമ്മയെ വിളിച്ചാ മതി മറ്റേ ഫോണിൽ. Okay, sorry, some urgent call. So you always converges to some quantity. For example, sin nx will not converge point wise, but sin nx converges to 0 in this weak sense, which is the average. If you take a sin nf function for a period, it will call average gets to 0. And you will also get some Hilbert spaces. Don't worry, this is some Hilbert spaces, and you get a u epsilon also converges to. This you can derive with some amount of PDE. So the question is that you look at this equation, this converges, this converges. Does this converge together? That's a question I'm asking. So the first term converges, the solution converges. Does this converges to this PDE? That's a very natural question. In other words, suppose you have two materials, copper and gold, with the conductivity properties alpha and beta. Equal amount I am mixing it. And 1 kg of gold, 1 kg of copper. Gold has a conductivity property alpha, copper has a conductivity property beta. I am mixing it thoroughly. So our natural guess is that the composite material will have a property alpha plus beta by 2 because you are equal amount you are taken, mixed equally, and then you will have a property. So that's not true. That's what mathematics tells you. The effective behavior will not be the average behavior, but then it has a behavior anyway. Okay, so for in a one-dimensional case, you will have a behavior something like that. So these are all bit more involved. If you are listening it for the first time, you will have a bit of a difficulty. Okay. The problem in the difficulty is the weak convergence. I told you this is not a standard convergence. This is a convergence in a different setup, in a different topology, in a different normed linear space. So if you have a Gn converges to G and Fn converges to F, in that weak sense, the problem is that the product need not converges to Gn. But at the same time, product may converge. For example, the sin nx 2 pi nx converges to 0, but if you take the product sin 2 pi nx into sin 2 pi nx, it doesn't converges into 0, rather it converges to half. So if you study this convergence in a weaker topology, weaker notion, it has its own trouble. This is a very general trouble, not just in homogenization. Many of the PDE problems have this trouble. So let me put it in what is mathematically. Let me put the same thing in a, I don't get into too much, it may be another couple of slides. That's all I will do it, because now it requires little more mathematics. So look at, so let me put it, let's forget about all PDE. Okay, so let's collect all matrices which is symmetric and also satisfies this condition. Those who are familiar with PDE or differential equations may easily understand this condition. Those who are not familiar, just take it as a condition. This is a matrix which is symmetric. That means Aij equal to Aj. This is a metric consisting of functions which satisfies this condition. Okay, we'll do that one. So this first inequality is nothing but what we call it a elliptic partial differential equation. But there is no differential equation coming here. So it's a collection of all matrices function which is symmetric and satisfies this condition. And once you choose an A, I can associate a partial differential equation here. Okay, so you see, given a matrix A, I have a differential equation here. And then my aim is to introduce certain convergence in the class relevant to the homogenization theory. That's what you are doing it. So AIJs are you are changing and you want to find the convergence of this PDE. So essentially you want to introduce a new convergence in this class of matrices. Okay, that is called what we call it a G convergence or H convergence. In other words, when I say that a class of functions Aj of epsilon, H converges, H is for homogenization, converges to Aij star as epsilon tends to 0 if U epsilon converges to U in H1 naught of omega, and this product converges. The problem is in this product, this will converge, but this may not converges to the product. It converges something to Aij star. It may not be Aij. So if you can find some matrix Aij star in such a way that the product converges to this, then we say that the matrix functions, the class of matrices converges to the matrix. Okay, here, yeah, this is what we call it. So this is a little difficult to understand if you are listening for the first time, and this is what mathematically we look at it. And what I have stated is one of the most simpler problem, nothing more than that. Okay. In other words, we have a family of differential operators and we would like to obtain the convergence of that. Okay, so we have a so in nutshell, you have a family of differential operators and we would like try to understand the limiting behavior of these operators. So that's what in a nutshell. So there are some compactness theorem, etc. theorem tells you that if you take any family, then there is a subset. So you always try to prove compactness theorems when you do that one. Okay. Yeah, these are all some technical issues. And then there is a theorem like that. So what I have stated is one of the most simpler problem. Now you will end up a simpler elliptic problem. You may have a Navier-Stokes equation, parabolic equation, hyperbolic equation. Your domains will be changed. Just one problem in the context of composite material is what I have explained to you here. So in a nutshell, one has a family of differential operators, and we would like to obtain the limit operator. In some sense, the limit behavior of the differential operators. The differential operators need not be elliptic. It can come from many other situations. But studying for elliptic operators is more fundamental even in other applications. So even if you want to study other types of equation, first in homogenization theory, you have to understand the easiest equation, easiest in that setup. Okay. So this is the last slide basically about the talk. The asymptotic analysis, understanding composite material, ground flow is a pretty old subject, maybe 100 years. Material scientists were constructing composite material for several decades. But the mathematical theory of homogenization started in the 1970s. It's a just 50-year-old subject. Mathematical aspects of mathematically understanding that. So there are various methods developed then, starting with any formal asymptotic expansions and energy method. This was introduced in the 1970s and early 80s. Then a compensated compactness is one of the important concepts, not just for homogenization. Studying other nonlinear partial differential equations also developed. And then there was a gamma convergence developed a little earlier. And this was developed to study optimal control problem, optimization problem, etc. And two-scale convergence or multi-scale convergence. So these are all, I said, deeper. You need a series of lectures. And then Fourier method, and then method of unfolding. This, and we are extensively using this method of unfolding. And I have given my series of papers. So I will stop here about my talk. And then there are these are all work of the last 10 years regard to oscillating boundary. And there are other work and there are books you can see. So some of the articles here. So if you go through some of the early papers, you will see some references for the talk also. Yeah, so we complete. Yeah, this is about nothing to do with my talk. I have some 2 books published. This is in 1970, published ordinary. These are both books are written as university MSc students in mind. So we have written this book because from people we hear that we don't have many books. So we have written these 2 books for our Indian university system as their master's textbook or a reference book. And I also given a video course about this talk about ODE, and new video course will come next year for the PDE. This you can hear. Thank you very much.
Thank you, sir, for explaining every minute detail so clearly.
1 minute. I will join in a minute. Just a few seconds. Okay.
Okay.
Giriraj.
Okay, sir.
Okay, Giriraj, I'm back.
Yes, sir. Thank you, sir, for explaining every minute detail so clearly. Very informative talk, sir. Now for question and answer, I hand over to Dr. Vivek.
Thank you very much, sir. for your
Okay.
valuable inputs to this webinar. Sir, we have received the question from the participant.
Mhm.
May I ask, sir? The
Yeah,
first
yeah,
question.
sure. I am here for that only.
Yes, sir. The first question is, sir, can it be applicable in heterogeneous data like the structures, semi-structures, and unstructured data?
It is not about the data I am talking. You, it is, but the problem in a overall view, yes, we are handling heterogeneous. It is a heterogeneous media we are doing. So what I described is a heterogeneous media. From the heterogeneous media, I want to understand the limit and get a homogeneous media. That's what I want to get it. How to apply for a data, one has to look into that. What kind of problem? So we are not handling the data. We are handling the heterogeneous media and the problems defined there. So I'm sure your heterogeneous data may be coming from the heterogeneous problem.
Yes, sir. And the next question is, sir, is this process of mixing uniform?
Need not be. I have given a most elementary way of mixing, but in practice, it need not be. In practical application, it need not be uniform. When it is not uniform, you may not have a uniform limit. You may have different subsequential limits. So if it is not uniform, in general, it's something like that. If you have a sequence, suppose you have a sequence of, even forget about PDE or anything. Take a sequence of numbers. That sequence may converge or may not converge, right? It may, and different subsequences may converge to different limits. So if the mixing is not uniform, you may have a different subsequential limits. You will have different subsequent. So if you have only homogeneous or some sort of a uniform, then you will have a uniform common limit, unique limit. Otherwise, you may not have it. Yes, but in practice need not be. It need not be uniform at all. For example, many of the grills you look at, the grill need not be uniform. But how do you know that which one is best? So there are many related questions. Yeah, that's a correct, good question. Need not be. But I have given that to show you something.
And another question is, sir, how it can be applicable for marketing the security model of data?
Oh, that I don't know. Marketing model. Definitely,
Yes,
I don't involve in that.
okay, sir. And the last question is, sir, how can epsilon value be infinite? Some students.
Not, oh sorry, maybe epsilon is 0. If that may be an error.
Okay, sir. Thank you very much, sir.
So it's when I write epsilon equal to, it's not that epsilon tends to 0. 1 over epsilon tends to infinity. So that may be maybe instead of epsilon, I've counted the number of cells. That number of cells go to infinity, not epsilon go to infinity. Okay, so it's an epsilon go to 0 basically. It may be a typo error in my thing, I think. Yeah. Okay.
Okay, sir. Thank you, sir.
Yeah.
Okay, thank you very much, sir, for informative talk. Now let me share with you brief introduction of today's second speaker, Dr. Joseph Rebenda. Dr. Joseph Rebenda is an assistant professor and researcher at Central European Institute of Technology, Brno University of Technology, Czech Republic. He also is an assistant professor at the Department of Mathematics of Faculty of Electrical Engineering and Communication of Brno University of Technology. Dr. Rebenda earned his PhD in Mathematical Analysis and MSc in Mathematics from Masaryk University of Brno, Czech Republic. Early in his career, he worked as a data analyst in a private company in the financial sector for 5 years. Later, he did his postdoc from University of Edinburgh, Norway. Dr. Rebenda has published many research papers in International Journal of Repute and conference contributions on topics of mathematical and numerical analysis, in particular stability and asymptotic properties of complex valued functional differential equations, a convergence of Picard type algorithm for partial differential equations and differential transformation. Dr. Rabenda's professional interests are mathematics, mathematics education, and higher education in general. Currently, Dr. Rabenda is involved in 2 national research projects and an international EU-funded project Platinum on communities of inquiry and inquiry-based mathematics education. We welcome you, sir. Dr. Rabenda will deliver a talk on ordinary, partial, functional, fractional, fuzzy, a survey on applications of differential transformation. Over to Dr. Rabenda, sir.
Please on your microphone. Yes, sir.
Yeah, thank you very much, Dr. Giriraj. So I will share my slides and please let me know if you can hear me and if you can see the slides, okay?
Yes, sir.
Okay. So this is it. So I hope you can see the slides. Sorry, I need the full screen mode. Yeah. So now it is visible, right?
Yes, sir, visible.
Very well. So my talk, as already has been announced, will be a talk about applications of the differential transformation to solving various types of differential equations. So before we start, first of all, I would like to thank to the web organizers, and that means Dr. Giriraj Mehti and his team at the Manipal University of Jaipur. So let us give a hand to the organizers. And thank you very much for inviting me to join this webinar. Then I also would like to reach out to the audience. So I've published a link in the questions and answers. Unfortunately, because I did it last minute and I couldn't include it in my presentation. So please follow the link in the question and answers. Actually, we can find it in the Teams and the questions and answers published. So you can see the link is active here. So please share this information, the requested information with me so that I can have an idea about what is going on. And then let us come back to the presentation, which is here. Yeah, here it comes. So let me just give a brief introduction into the topic. So sometimes in the science we are moving in 2 directions, and it can be either vertical or horizontal. So many colleagues are dealing and going into the vertical direction, which means that they go deep and deep into one topic and into one topic and do more and more detail and so on. Sometimes it is also convenient to go more horizontal, and that means that we try to connect different parts or different topics with one common view or point of view. And that would be the case of my talk. I want to go more into the horizontal point of view to cover several types of differential equations, not to go deeper in one type, but rather to make it more horizontal. So let us start with something really basic, and that is Taylor's theorem. So everybody knows this, and usually This is the topic which we teach in the first semester at the undergraduate level. So let us recall what does this Taylor theorem says. Under certain conditions, which are listed on the slide, we can write a function which has a certain amount of derivatives at point x0. We can write as a sum of a polynomial and a remainder term. And that's what I hope everybody here knows. And how we can use it in solving differential equations. So let us introduce the differential transformation. What is it? The differential transformation. So we take a real function and a real point on a real axis, so we call it t0. And then we define the differential transform. We transform the function, which in principle is continuous and has, say, some continuous derivatives. We transform it into a sequence of numbers. And these numbers represent the coefficients. In fact, as we can see on the right-hand side, these coefficients are, the numbers are coefficients of the Taylor polynomial or Taylor series. So this is the principle, and then usually when we do a transformation, we need an inverse transform. So the inverse differential transform is that we take the sequence of numbers and we build up a Taylor series or Taylor polynomial, depending on how many of the coefficients do we have, in this way. So we build up the Taylor series. Of course, in practical applications, we usually use computers. And thus we are limited to a finite number of coefficients. So in applications, our function is usually approximated like this. And that is the basic idea of the differential transform. So we have a transform, we have an inverse transform, and now we can talk about properties and applications as in the same way as we do for a Laplace transform or a Fourier transform and other type of transforms. So usually in the transforms we have some formulas which represent the grammar and vocabulary of the language of the transformation. So let us review some basic formulas which will be applicable, which are applicable in solving the differential equations. So here we can see what is the formula for transforming an nth order derivative of a function. Then we have a product, which can be generalized to a finite number of functions, of a product of finite number of functions. Then we also can see and compare the transforms of power function t to the power of n at point 0 and at other arbitrary real point. And then we also will use, or we will see the exponential function in applications in the example. So that's why we list it here. Then it is a good time to have a look at our form, which I hope has been filled by the participants of this webinar. So let us have a look at the answers. So it looks like most of the participants have experience with ordinary and partial differential equations. Then significantly smaller part of the audience have experience with other types, which I have listed here just in case, just for my curiosity. And in particular, it seems that there is the least of the participants in the audience have ever worked with the delayed or retarded differential equations, which is a type of functional differential equations, and that that is a kind of pleasure for me that a part of my talk is devoted, focused on delayed and retarded differential equations. So let's get back to the outline. So we can see here that we will see some applications or examples of ordinary, partial, and functional and fractional differential equations. So let us start with the basic and simple examples and simple applications. So our goal is to find an approximate solution to an ODE of generally of order n, as we can see here. And for such ordinary differential equations, we also need initial conditions. And we assume that the function f on the right-hand side is an analytic real function. So sometimes, and I don't specify where it is analytic on purpose, because that's a good type of question which usually arises. So let us think about where should be the function analytic. I don't think it's too complicated, but it's a kind of engaging question. And now let us have a look at the differential transformation of the equation, because similarly to the Laplace transform and other types of transform, we transform the original equation and then do some arithmetic manipulation or algebraic, as we do with using Laplace transform, and then we do the inverse differential transform, as we do with the other transforms. So the transform equation has the form of the equation number 6. So we also will need to use the initial conditions, of course. So we have to transform them too. And here nothing changes much. The only thing is that we have to keep in mind that there are factorials when transforming the conditions of order of the derivative 2 and higher. We need to divide the coefficient by the factorial. So that's one of the common mistakes which I have done sometimes before I learned not to forget to do it. So let us take a simple test problem, and in fact it's the simplest problem ever. So we have equation 8 and initial condition at 0, which is equal to some real number c, real value c. So when we apply the differential transform to such equation, then we get equation 9, and we, of course, because it's a recurrence relation, so we want to have the number, the coefficient which we want to calculate or compute, we want to have on one side, and all the rest of the known values we want to have on the right-hand side. So that's what we do here, followed by the arrow, following the arrow. Then initial condition doesn't change. There is no change in the initial condition. So we can start calculating. So the first coefficient is again c, then the second one is c divided by 1 plus 1, which is 2, and we continue so that we can see the pattern. And the pattern reveals that indeed, if we attempt to write the Taylor polynomial, then actually we see that what we got is a Taylor or better said, Maclaurin series of the function of the exponential function multiplied by the real constant c. So this is the simplest problem, just to have an idea how the whole thing, the differential transform, works in applications. So I repeat it once again. First, we transform the equation to the form 9, and by doing this, we receive a recurrence relation. So this is a good news for those who want to practice in scientific computing, because recurrence relation is one of the common approaches, and it's not difficult to program such an algorithm. So this is what happens here. And now we can move to partial differential equations. So for partial differential equations, then of course we need some modifications, because, or modification at least, because now we have two independent variables, t and x. So the definition of the differential transform is now different. We see that again it is a sequence of numbers, of real numbers at this stage, at this point, but those real numbers, or this sequence, actually is a two-dimensional sequence, which means that we can write the coefficients in an infinite table, two-dimensional table. And now, how do the coefficients look like? So again, we have a formula for calculating the Taylor coefficients of the function u at point t0, x0. Then the inverse differential transformation has an expected form of a double sum, which is the best case if we can guess the Taylor series. But in most cases, in most applications, again, we will be looking for an approximation of the solution, and that means that the number of the coefficients we are able to calculate or compute is finite. So that's what again we can see here. But now we have a Taylor polynomial in two variables as expected. So let us have a look how the algorithm works for PDEs. So our goal is to find approximate solution to an initial value problem, and because we are talking about the initial value problem, we can consider only a certain types of PDEs, and we have these two types. So for just for example, to have an idea what is the type, we have a heat type equation and a wave type equation, which we could also call parabolic and hyperbolic types. So we are not discussing here an application to the elliptic partial differential equation, elliptic type, because we are talking about initial value problem. So for elliptic type partial differential equations, we would have to consider boundary value problems, and this also is possible. It also is possible to apply a differential transform to boundary value problems, but this is not, it's not the topic of this presentation, so we can discuss it later, maybe. So again, the right-hand side of the equation we suppose is analytic, real function, and we again need some initial conditions. This time, the initial conditions themselves are functions of one variable, as expected. So we can also expect that what will happen. We will have to transform the whole equation and also the initial conditions again. So let's have a look what can be the form, what form can take the differential transform of the equation H. So here we can see, because the equation H has a derivative with respect to t on the left hand side, then we also have the shift. The transformed formula has a shift k plus 1 in the first variable, first independent variable. And on the right hand side, where there are derivatives with respect to x, we can see that there can occur shifts in the second independent variable, which are represented by those formulas h plus 1, h plus 2. Also, we need to transform the initial conditions. So this time, the initial conditions will be not only the real numbers, but they transform. We have to transform the function, so it will be a sequence of real numbers. Transformed initial conditions will have the form of a sequence of real numbers. So let's have a look at some simple test problem again. So consider the equation 15, which by quick inspection we see is a wave type equation or a hyperbolic type of PDE. And we have two initial conditions because we have the second derivative. So now we apply the partial differential transform to the equation itself, and we get the recurrence relation number 16. And we also transform the initial conditions, which will give us, well, we use the Kronecker delta symbol here. So this function is non-zero only if the argument is 0, if its argument is 0. So we can calculate first few coefficients, and we can see that that for u something 0, everything will be 0. So we start with h1, and that is represented by u21. So this is the first coefficient, which is non-zero, and we see it is 1/2. Then the next non-zero coefficient is u31, and so on, u41, and so on. So continuing like this, we can again write the Taylor polynomial for the approximate solution, and we will see that there is only one x, and it x to the power of 1, and then all the rest of the coefficients, all the rest of the numbers can be collected in one term inside the sum, so we have the function which is an exact solution. I would say that this is rarely what we will get in the real-life applications, but we can use it, and I usually use it to such test problems to see how the algorithm works and whether it works correctly or not. So here we see everything works fine. Then, sorry, the next application will be for function differential equations, and that is what I was talking about. That is the delayed differential equations. So we have a functional differential equation of the nth order in general, and here we can see that there are constant delays denoted by tau1, tau2, and tau r. So we have r delays which are constant delays. So our function The functions in bold are vector functions containing the delays. And also there is an important condition that all the derivatives are less or equal than n, because if some of them is higher than n, then it is an equation of advanced type, and the whole theory for retarded or neutral differential equations doesn't work for equations of advanced type. So this is an important condition. Then again, we assume that the right-hand side is analytic, real function, analytic real operator. We have the constant delays, we have R of them, a finite number. And then we also would need to calculate the maximum delay, the maximal length of the delay, and also the maximal derivative in the delayed terms. Of course, for such differential equations with delay, we will need an initial function which is prescribed on some interval which is prior to our initial point t0. So that's why we needed the maximal delay t star, because of the initial function. So let us have a look how we can deal with that. Just recall the equation and the initial functions. How to deal with it? So I was reflecting about how to correctly approach this type of problem with the differential transform, and it took me about half a year. And then one day I was resting, relaxing like that, and then I got the idea, what if I try, what if I can combine this with the so-called method of steps? What if I use the method of steps? And this means that we take the initial function and place it instead in the places of all the bold type functions where the delay terms appear. And what will happen then? What happens is that equation 17 becomes an ODE. So this is not, I would say, absolutely new idea. This idea is more than 50 years old, but nobody actually tried it with the differential transform. What I have seen in the papers before I came with this combination was a formula for shifted arguments, and we will see later how it looks like and what the results does it can it produce if misused. So let's have a look at how does this combination of the method of steps and differential transform works. So if we combine those two methods, we obtain a recurrent algebraic equation or relation 18, and also we will have initial conditions which we have to transform, and this time they are constants, they are real constants. So again, we have a recurrence relation, we have some constants which we feed in the recurrence relation, and we can calculate the solution. So then the solution is then constructed in a standard way by using the inverse transform, but there is a hook, a hidden hook. The solution is only valid on some relatively small interval, t0 from t0 to t0 plus alpha, where alpha is the minimal constant of the delays. And that's what we do on this small interval. But now we usually want the solution to find the solution on a longer interval. So what we can do? I decided to split the the idea or the algorithm for two cases. One is the case of the commensurate delays, and then we will also have non-commensurate delays. What does it mean, commensurate? It means that there is a special relationship between the delays, mutually between every pair. So if we divide them, we get a rational number. So that means we can have rational delays or integer delays in the equation, but it also can be that we have the equation where we have numbers like pi, and there will be the delay like t minus pi and t minus 2 pi and t minus 3 pi and so on. And that algorithm would still work because pi, 2 pi and 3 pi are commensurate numbers. So if all the delays are commensurate, then we define a certain numbers depending on the commensurability, of course. And we also split our interval from t0 to t, where we want to find the approximate solution, into smaller intervals of the length a star. And then that's in this way we get the intervals I with the subscript j, and the last one we denote I k plus 1. So we are looking for solutions u with subscript j on the individual intervals, on the consecutive intervals. And again, on each of the interval, what can happen? Either the bold typed functions will fall into one of the prior calculated intervals, and that's good because we already know the approximate solution on that interval, or if not, it can fall also below t0, and in that case we replace the bold typed functions with the initial function phi again. So in all cases, on all the intervals which we calculate or which we are looking for a solution one by one, we have an ordinary differential equation. Sorry for the squares. But again, it's a recurrence equation with constants we can feed in. So what we do is, and what we also can say is that if the case happens that the bold typed functions should fall into one of the previous intervals, not below t0, then this lemma, we have a lemma, which is a useful lemma, which tells us that we can actually use the coefficients of the Taylor polynomial, which we have calculated in one of the previous intervals. And that again is a good news for scientific computing, because it means that we don't have to calculate those values again. We just take them out of the memory and use them in the next intervals. And I think this idea again is one of the popular ideas or commonly seen ideas in scientific computing. What do we have here is the 4 question marks here. So the question is, what should be here? And I didn't put it there because it would destroy the nice equation as it is now and disrupt into 2 lines. So I just omit it, and we can guess what should be there. And yes, most of you are guessing correctly, because you see there is the subscript L. So if, as the condition is, this value falls within this interval I with subscript L, and we have UL here, then what should be here should be T0 plus L minus 1 A star. So that's it. And then the solution, sorry, there is S missing. The solutions Uj then has a form of as we can see here. So this is like the point where we do the transformation, and then it makes it forms the Taylor polynomial or Taylor series in the best case again. And then the complete solution, approximate solution we are looking for would have the form of several solutions, several functions, actually k plus 1 functions, which are stick one to each other at the end point of the intervals. So the solution on the whole interval from t0 to capital T will be a continuous function. Then what we have here is, as I say, the algorithm was split into two cases, and now we come to the case of non-commensurate delays algorithm. So basically we involve irrational numbers here, non-rational numbers. So if there is at least one pair of the delays which are not commensurate, so I mean if their ratio is not rational number, then again we have to define some constants, and we do it like this. We find all ordered R tuples which satisfy the condition that T0 plus K1 tau 1, which is the delay, one of the delays, and so on. So such sum is less than the capital T, which is the end point of the interval where we are looking for the approximate solution. So that's the first step. We find the R tuples, then we arrange them in ascending sequence so that we can have a sequence of points, actually endpoints of the new intervals. And these intervals, again, we denote I with subscript j. So we have such a sequence, a finite number of intervals, and the last one again ends with the capital T. Then we again are looking for solutions on these intervals, and again the same thing happens as for the commensurate delays case. So the delayed terms fall either into one of the previous intervals ij, or they fall below t0, and then we replace the bold typed functions with the initial function. So this is the same part as in the previous. Then again we have a lemma here, because we need to know how to calculate the coefficients from the previous ones. And again we have a lemma here, but in this case you see there is a strange term like this. And this is because it may happen that sigma j minus 1 and sigma l minus 1 will not be commensurate, and then and also tau I. So then there will be some multiplying factor. And again we have a question mark here. So what do you think should be placed here? So when we look at the part here, UL, And then we see that this number t minus tau I falls into the interval IL. So this question mark should be replaced by the initial point of the interval IL, and this is sigma with the subscript L minus 1. So yes, you guessed it right. Then again, the solution has the similar or the same form as in the commensurate case. And again, we will have a sequence of finite sequence of solutions on each interval, and these solutions again will meet each other at the endpoints of interval. So the overall solution UT will be continuous. So this is the theory, and let's have a look at a few examples so that we can see how this actually works. So let's have a look at the following linear equation with two delays which are commensurate. The delays are numbers 2 and 3. So we also have an initial condition and an initial function which is constant in this case. And we have to consider the initial function on the interval from -3 to 0, because if we put 0 to the equation, we replace t by 0, then we will have u in at -3. So this is what we have to do. We have to prescribe the initial function to the past, so that the whole equation is covered. Then the greatest common divisor of 2 and 3 is 1. So, and we are looking for the solution on the intervals 1, 2, 3, and so on. So we also need to transform the initial condition. It will be 1, the constant. And we also transform or replace, because t minus 1 falls below 0, so we have to replace u by the function phi here, and it gives us constant 1. The same with the second term, and we see that the transformed equation now looks very simple here, because in fact it's the equation u prime equals 2 minus 1, which is 1, and this is the transformed version of the equation. So with the initial conditions we can calculate the coefficients, and we see that everything starting by 2 beyond 1 is all the coefficients are 0, so the solution on the interval I1 is nice function 1 plus t. Then we come to the second interval, and we see that the transformed initial condition is we have to calculate it at the endpoint of the interval I1, which is 1. So 1 plus 1 is 2. So that's the reason for the number 2 here. Then again we see that if we replace t by real numbers from interval I2, which is from 1 to 2, then we get below 0, so we replace the functions on the right hand side by 1. We see that the transformed equation has the same form, so it also has the same coefficient, and it also gives the same solution, although this time it is written in the form 2 plus t minus 1, because the starting point of the interval I2 was number 1. So we can continue like this for further intervals, like the interval I3, and here we see that for the first time the term t minus 2, the function u with the term t minus 2 falls within the interval I1. So we have to take this into account and then replace this function by 1 plus t minus 2. And the other term with t minus 3 remains the same. Then the transformed equation has changed a little bit. Now we have two terms on the right hand side. So what we can also expect, there are two coefficients. So coefficients up to order 2, and everything beyond is 0 again. So the solution has the form of quadratic polynomial, which can be written in different forms, of course. Then on the interval I4, we see that both functions now, the one including t minus 2 and the one including t minus 3, are replaced by the functions from interval, the solutions from the interval, the second and the first. So the transformed equation has again two terms, and again the solution on this interval, on the fourth interval, will be a polynomial of order 2. So let's just do one more step. So let's have a look on the interval, the fifth one, so from 4 to 5. And here we will see that there are actually three non-zero terms on the right-hand side of the recurrence relation. So we will have non-zero terms up to order 3, and we will have the polynomial of order 3 as a solution. And it can be verified that by the regular method of steps and just integrating, just finding antiderivatives or using standard integration, that these solutions fit very well. So the whole point is to again verify that the algorithm works well, works precisely, and can be implemented in a computer code as a software. Then we have an example of what can happen if we use a shifted arguments formula, which has been used in the literature before I used the idea of the method of steps. So here we can see how the shifted argument formula looks like. And now again, let's have a look at the same example. So let's have a look how it looks like when we use the shifted arguments formula. It looks absolutely totally different. We have two terms only, but they are much more complicated than those Diracs, which we had when using the method of steps and the differential transform, this combination. So also we can compare. We have to limit to a finite number of coefficients. Then, for example, if we choose n equal to 3, the upper bound of the sum will be 3. Then we obtain a set of linear equations, and by solving this, we get the coefficients and we get a totally different result, which in fact is not a solution to the given Cauchy problem. So this is what I have seen in the papers, and I was puzzled because this idea didn't work for some Cauchy problems, which I found in other papers and in literature. So that was the reason why I started to look for something correct and efficient. And then also we have an example for non-commensurate delay. So this will be more general, not as concrete as the previous one. So let's have a look. This time we need an initial function on the interval from minus pi to 0, because pi is greater than 3. we want to find the solution on 0 on the interval from 0 to 9. So we name our constants, then we find the R tuples, which actually are pairs, ordered pairs in this case, and we see what numbers are these ordered pairs. So we have 0, 3, pi, 6, 3 plus pi, and 2 pi, and then the last one, the final one, is 9. So that's how we compose our intervals I1 from I1 to I6. And then we can just write down the form, the general form, how the equations itself would look like on each of the intervals. So here you can see that on the first interval there is a function g on both places. For u2 on the second interval only one, and so on. We go further and further. Sometimes there can be both functions the same, as we see on the interval u6. So the transform system again is just for you to have an idea. So we have a nice recurrence relations, like for the cases of I1, I2, and I5, but also we will have here the multiplying factor, as I was talking about this already. So in I3, I4, and I6 we have these factors, and they always should be in greater than 1 in absolute value. So let's just a brief info about the fractional differential equations. So for fractional differential equations, for instance, and then Fowler type equation, we have to define what does it mean to have the fractional derivative. So in my papers I work with the Caputo derivative, or the fractional derivative in the Caputo sense, which means that the derivative here is behind the integral, inside the integral. Then we suppose some conditions, assume some conditions on the functions f and g, and also we need initial conditions. Why do I write only 2 initial conditions? That's because we require that the beta is less than 1, and that means that the order of the equation is not greater than 2. So we only need up to 2 initial conditions. And we look for a solution for t greater than 0. We need to find a new definition for the fractional differential transformation. So we use a subscript alpha here, because we need to say what is the order. And here we see that the form...
Limitations of differential transformation.
Excuse me? Is there any issue with that? Oh, no. Okay, so the definition is similar to the ordinary differential equations, only here we have a gamma function replacing the factorial, and we have a fractional derivative replacing the standard derivative. The inverse differential transform again is as expected. This time we don't have a Taylor or Maclaurin series, it's a fractional power series, because here we can have fractions, I mean square roots and so on. So again, in practical applications, we are looking for approximation. So there are transformation formulas which differ a bit from the ordinary differential transform, and the most important one is again the formula, the last one, the formula for the derivative, the transformation of the fractional derivative. So we have a vocabulary, we have the grammar, and we need to know how to determine the order of the alpha. Why am I talking about this? Because again, in many papers I have read about the fractional differential transform. There is no idea, no hint, no algorithm how to determine the order alpha. So that's why I'm talking about this. So let's suppose that the equation is strictly fractional, which means we have only a rational derivatives, rational number derivatives. Then the order alpha should satisfy these three conditions. It should be less than 1, definitely, between 0 and 1. It should be a multiple such that it hits beta, multiplied by some natural number, and it also should hit 1. So then the third condition is because we want to use the initial conditions, the how to say, integer order initial conditions. Of course, we have infinitely many choices, but there always is a possibility to find an optimal one. So in the case of our equation, the reciprocal of the denominators of 2 beta and beta, which is q. So alpha is 1 over q. That's the optimal choice I suggest. Then we also have to transform the initial conditions, and that goes in a standard way, as for the standard integer order differential transform. And we can see how does it work for our Lane-Emden type equation, which can be found on Wikipedia. For example, the solution of this equation can be found on Wikipedia in integer order. So we have transformed the coefficients. Now we transform the equation and we can calculate the coefficient, and we see that all of them are 0 except the multiples of 2p. So 2p, 4p, 6p, and so on. So then we can write for beta equal 1. That's the case which you can find on Wikipedia. The coefficients have the form of standard factorials. So we can see, or we can see the pattern which leads to the exact solution, which actually is sine t divided by t. So we are coming to the conclusion. So let's see the comparison, how we can compare to the other algorithms. So consider this neutral system of neutral equations, which is very highly nonlinear, and also there is a non-constant delay. So it's also can be done via differential transformation. So the transformed system has again a form of recurrence relations, and this can be calculated. The coefficients can be calculated in the computer, but we can also do it by hand. And here we see how do the approximate solution look like. So the first one contains some expressions including exponential, while the second one is a polynomial, and that's nice, that's better news. So let's have a look at the values, compare the values obtained by a reference method DDENSD in MATLAB, standard routine. So we can compare and we can say that the values are quite realistic and quite close. And what about the computing time? Well, my colleague who did the calculations reported that the differential transform has been 3 orders faster than the MATLAB routine. Well, I didn't do it myself, so I have to trust him, but anyway, it looks promising indeed. So let's conclude, give some summary. So The differential transform can be applied to various types of differential equations, and we have been talking about initial value problems, but it also can be used for other types. The algorithm is easy applicable, provided we can transform the equation. Then the approximate solution has a good convergence properties, and it's because it's based on a Taylor series. So everything which converges in Taylor theory converges here too. Another good thing also is that if we divide the interval into smaller steps, like to have smaller grid, and then we just have the need to get approximate solution of something in between the grid points, then we can do it because we have a smooth function. This is a different approach than we use at standard methods like Euler or Runge-Kutta, and that's an advantage. So we can find approximate values at the whole interval of which is considered. Sometimes we are able to identify an exact solution, but this is a rare case, so I will not elaborate on that more. The good thing is that we don't need an initial approximation, I mean not initial guess approximation, because we have the initial conditions and they are given, they are set. And one positive news for, again, the scientific computing is that all the time we use arithmetical operations. So no symbolic or numerical integration or differentiation. That's good. And as we could see, it also can be applied to nonlinear equations, but that's for another talk. It's not possible to include it to this one. So what are the challenges as I see it as of today? So we can work on generalizations of the transform for, say, nonlinearities, independent variable. That's what I have been talking about, and it's already done. So those one which are in black have been done, and some also published. It can be used for distributed delays. That's also done. I have done this, and it's realistic. We can work with non-constant delays. So I have worked with non-constant time-dependent delays, not yet on state-dependent delays. So this is an open problem for me. We can apply the differential transform to other types of problems, for instance, boundary value problems. That's what I have used to, and I have a few publications on this topic. Fuzzy DEs, that's work which has not done by me, but I have read several papers where the authors, the scientists are dealing and successfully dealing with fuzzy DEs. And again, we can think about random or stochastic ODEs or functional differential equations. Why? Because also for random and stochastic equations, in that theory, we also have something like Taylor theorem. It's called Ito formula, I think. So I was thinking about generalizing the differential transform to these types of problems too. And again, also an idea is to make it a continuous, which means an integral differential transform, a kind of Laplace or Fourier transform where we can see the integrals. And I'm working on this currently. And then we can discuss also variable order derivatives and so on. And of course, last but not least, we can always think about complex numbers. So that's the challenges, and I think that's all I wanted to discuss for today. So just to have an idea of recent publications in this field, so that there are publications on the delayed differential equations and also with equations with time-dependent delays, and also fractional differential equations with commensurate and non-commensurate orders. So that's already covered. So thank you very much for your attention. And then what I would like to do in the end is if I may ask you to make a cross or a dot at the place you live or work in the map of India, that I would be delighted. So I will place this into the links so that after the seminar I can see where all the places. Thank you very much, and now I think if there are any questions, feel free to ask.
Thank you very much, Professor Rabinda sir, for very informative and knowledgeable talk. Now for question and answer, I hand over to Dr. Vivek.
Thank you very much, sir, for your valuable input to this webinar. We received the question from the participant. The first question is, what are the best analytical numerical method to solve capital differential equations?
Excuse me, may I ask you to repeat once again, because I didn't hear well.
Please, Dr. Vivek, please unmute your
yes.
sound. Dr. Vivek, please unmute.
Sorry. Thank you, sir. Thank you very much for your valuable input to this webinar. We received the question from the participants. Sir, what are the best analytical and numerical method to solve capital differential equation?
What is the best analytical numerical method, right? So shall I pick one analytical and one numerical method, right? That's the question. Okay, so for me, the best analytical method to solve differential equation is dependent on the type of the differential equation, of course, but they are differ for ordinary and for partial differential equations. But as I have told, for the ordinary differential equations, some integration methods, also method of steps for the delayed equations is a good one. And for PDEs, well, I've learned the method of characteristics, and that's it. So far for numerical methods, I have used some Runge-Kutta methods, and but the last several years I work with Differential Transform as a numerical or semi-analytical method. So that's the one I work with. So that's my favorite, of course. And for the PDEs, there are basically 3 of them, and I have no favorite because I don't. I didn't work with PDEs much. I was dealing with some Banach type fixed point theorems and Picard schemes and so on. So that was a kind of analytical one for PDEs, which I used and worked with to prove some existence and uniqueness results.
And another question is, what are the limitations of differential transformation method?
What are the limitations, right?
Yes, sir.
Okay, so far as I know, the limitations are the same as for the Taylor series methods, and that means that we have to be careful about the region of convergence. And I was not talking much about the mesh grid, but what we do with a standard numerical method, that we divide the interval into a mesh grid, that's what I would suggest to do for differential transform too. That's good for the convergence, to improving the convergence properties. There also are different forms possible of the differential transform, at least one. which resolves this issue by scaling. It scales the whole interval within the interval from 0 to 1, and then you perform the calculations there and then rescale again to the whole interval. It's not a big difference, but it can make some difference in precision.
So thank you very much, sir, for your valuable input.
Now for vote of thanks, I hand over to Dr. Rishikesh.
Namaskar, honorable professors, industrial persons, students, and my dear friends. Good afternoon to one and all. On behalf of Department of Mathematics and Statistics, Manipal University, Jaipur, Rajasthan, India, I, Dr. Rishikesh Tiwari, deem it a great honor to propose the vote of thanks to all of you for being connected with us in making this webinar such a resounding success. I would like to extend a hearty vote of thanks on behalf of Manipal University, Jaipur, to our respected and most distinguished speakers of the day, Professor A.K. Nanda Kumaran, Department of Mathematics, Indian Institute of Science, Bangalore, and Professor Joseph Rebenda, Department of Mathematics, Brno University of Technology, Czech Republic, for making this webinar interesting and meaningful. I would like to express our profound gratitude to our respected Dean, Faculty of Science, Professor Anup Kumar Mukhopadhyay, Director, School of Basic Science, Professor Lalita Ledwani, Head of the Department of Mathematics and Statistics, Professor Kalpana Sharma, for providing encouragement and supporting mightily to organize this event. We are extremely overwhelmed by the response of the registered participants. I would like to thank all the wonderful participants from India and abroad who have turned up in such a great numbers. In all, 1100 participants were registered. I would like to congratulate the conveners of the webinar, Dr. Giriraj Methi sir and Dr. Vivek Singh, for smoothly organizing and making this event a great success. Each certificate will be provided to the participants within a week. Once again, I thank all of you for your cordial cooperation. Namaskar.
Thank you very much.
Thank you.
Again, I am personally grateful to Professor A.K. Kumaran, IS Bangalore, and Professor Joseph Rebenda, Bharati University of Technology, Czech Republic, for sharing very informative and knowledgeable talks.
Okay, thank you. Bye,
Yes, thank you very much.
Thank you very much, sir.
Thank you.
Nice
Thank
to
you, sir.
listen to your talk. It's good, well presented.
Yes.
Brenda.
You too. I liked it.
So, when everything is over, you can visit India sometime.
Well, under current circumstances, it doesn't look like that. But I hope that after the situation will calm down, that one day it will be possible. And actually, I was surprised because in the first moment I didn't realize, but then I have looked at the name of the university, Manipal University, Jaipur, and I told myself, Jaipur, it's familiar to me. Where did I see that? And then you could see the picture in my presentation. It's this one. It's a game. It's a card game, and I love to play it. So that was what I that I realized that it's not the first time I hear about Jaipur.
Thank you, sir.
Thank you very much, sir.
Thank you very much.
Yeah. Yeah, you're welcome to India. It will be over in another few months or maybe a year. That's all. It can't go beyond that.
Yeah, I think so. First, we have people let calm down a little bit, and then we can plan some.
We get a medicine by the end of the year.
Yeah, I hope so. But of course, I was very pleased that we can